Okay, so we know we have a few participants from all around the world. Actually, we have seen that there's people from Asia, from Europe, from other continents, and also our speakers represent quite an international panel. So at this point, without further ado, I would actually give the word to our partner, Anton Ellenbroek from the FAO Fisheries Department. So Anton, the floor is yours, and feel free to introduce the work that we're doing.
Yes, good morning, everybody. Understanding now that we are a global audience, maybe also good night, good afternoon, or good day. Also, Anton Ellenbroek. I work at the FAO of the United Nations in the NFI-SI team, so the Fisheries Knowledge and Information Management team. And we were asked to present to the site in Innovation Forum through a side event some of the work that we do in aquaculture. So we are only a small part of the Fisheries and Aquaculture division, but we do some research together with funding from the European Union, the Horizon 2020 project. And today we will show you like 2 examples of some of the work that we have done during the past 2 years. It is a research work, so we are not working really hard with countries or projects to already implement what we have done. So we thank the EU for giving us this research opportunity. We think we've come quite far with developing relevant services for the aquaculture sector, but it is for others to pick up on the research and innovation progress we've made, and to further implement the results of our project activities. So I'll start sharing my screen. If Federico, can you confirm that it is all visible?
Yes, it's working.
Okay. And we wait 1 more minute before I start the presentation. So the Science and Innovation Forum, it officially starts next week, but the side events, there's many of them. So check online if there are more side events that you are interested in. And it is a big forum about harnessing science, technology, and innovation for transforming our agri-food systems. So it's a much wider scope than what we will present today. Today we will present in our side event aquaculture detection with remote sensing. And then after we have detected the aquaculture, how do we transfer this in an innovative way to a global audience that might be in need of services to monitor their aquaculture sector? And with aquaculture sector monitoring, I mean today detection of cages, so ocean cages floating on open water. And then a next phase is a detection of aquaculture ponds intermingled with rice fields and other land uses, where we have an example with using artificial intelligence and machine learning from Indonesia. The work was done through a digital innovation, was the result of a EU Horizon 2020 Blue-Cloud project. It is a EU flagship project. It will end next year in March, but there is already a follow-up project formulated that will be Horizon 2020, no, Horizon Europe Blue-Cloud 26. And in that Blue-Cloud project, so the current project, we had a task to develop an aquaculture atlas as a demonstrator, which means we had to come to a maturity stage where the entire workflow is ready and operational and led to output. So we needed to validate our output, and for that we invited an expert from Indonesia. He's here with us today, and at the end of the presentation he will show you how he managed to validate the outputs of the analytical work done by CLS in France. So the Aquaculture Atlas, the demonstrator, will be introduced to you today by Dr. Jeremy Augot of CLS in France. You already know who I am. And then from NRIA, Dr. Tarunamulia doing the validation work. So what is this Atlas demonstrator exactly? It is an innovative use case across stakeholders. So we tried to work with CLS France as the analyst, so developing the data analytics. Then FAO's role was to be the integrator, so we did the integration in a spatial data infrastructure, and we worked to put the analysis in context. So we had a map produced by Jeremy, but what does it mean in terms of distances to production sites, or could we merge and show this in context with other geospatial data? And then Indonesia was the validator where they did the ground truthing and cloud truthing. So what we did wasn't relevant to what was observed in the ground, but also what is the value of this thing in a cloud environment. The innovative collaboration aspects was that we worked with a lot of Horizon 2020 Blue-Cloud partners. So we had CLS for the analytics with the FAO and FISI team, the experts from the knowledge and information team working to integrate the data. But we also worked then with the Indonesian National Research and Innovation Agency for the validation, and then a CNREC in Pisa that provided the VRE technology where if you want to have it very root, it would be one platform to rule them all. So all the data are brought in that platform, but also the users are managed in that platform. The integrations are managed through that platform. So it's quite a capable cloud-based environment for data analytics also for the aquaculture domain. Also a special thanks to all the contributors. So we discussed what we did with, for instance, the FAO geospatial data team of CPAL, and they were very helpful with getting geospatial data for us to experiment with. And also PlanetCom, the data outreach team, helped us with some data sets that we used and tested during the course of this project. So the innovation is a cloud-based approach to geospatial detection and also data integration. So we used 3 Copernicus Sentinel data in the end, and then we brought that together in the Blue-Cloud platform, so the D4Science platform e-infrastructure of CNREC in Pisa. We used, for example, also a Jupyter notebook, but also a lot of R, and we represented data using R Shiny, but always in the same platform. So this whole integration issue in this using this e-infrastructure was really a step forward, an innovative step in bringing data from the satellites in the hands of people that do the analysis and do the spatial planning. So all results are stored in an ISO OGC compliant spatial data infrastructure, which happens to be the same, exactly the same infrastructure that we also use for other demonstrators, for instance, a fisheries demonstrator, and that is also used for other VREs, virtual research environments already used by FAO. All results and products are in the demonstrator phase, so please do not judge us too harshly if you say, well, I do not see the real results, because we try to build a case, but we did not try to implement a case. But we are ready to be adapted to real use cases that you may come forward with after this fantastic presentation on the demonstrator. So the use case, what did we do? So we work with CLS, collect localisation satellites. Thank you, Jeremy, for my compliment on my French. To focus on the data analytics. And Dr. Jeremy Augot, he will be the next presenter. He will show you more details on the data analytics that he performed. Then with the Indonesian Research Center for Fisheries, National Research and Innovation Agency. So we had one expert collaborating with it. It was not at the level of the research center, but an expert from that agency helped us to focus our results validation. So how could it be? How useful were they in terms of the data quality, but also how useful would they be if we would propose this type of analysis for a real research work? And Dr. Tarunamulia will explain a bit how he did the validation of the results. So FAO's role in this use case was to integrate the output in an atlas built on a virtual research environment. Again, the Blue-Cloud technology that is developed through this EU Horizon 2020 project, in particular with a lot of input through CNREC in Pisa. So our atlas shares a lot of technology with the Fisheries Atlas, so we could only develop this project by having a shared data viewer that uses a lot of components that we developed for the Fisheries Atlas, and we rely on an open fair viewer and ISO OGC services for the spatial data infrastructure. This atlas is extendable with other components, and we will show you later how we managed to do that, for instance, with statistical widgets and an R Shiny app to quickly show your results to end users. So this innovation enables cross-domain collaboration in one platform, and I think that is the real innovation that we achieved in this use case. A real collaboration on a real platform, but across different teams and across different domains. So this Blue-Cloud collaboration resulted in 2 workflows in the cloud that will be introduced later again in more detail by Jeremy. But the first one is a Jupyter notebook to facilitate data management of Sentinel-1 data for cage detection. And then the second approach was to work with an Indonesian consultant on the validation of an artificial intelligence and machine learning map that they did for pond detection by a land type classification algorithm run over Maros in South Sulawesi. And then FEO NFIS, I used its OGC metadata-driven approach to bring this data back together and show this along with the same technology that we used in the fishery demonstrator, so cost-effective. And then that result looks a bit like this. So we receive some data over an area, we have an area of interest, and then we use shared components. So these are statistical widgets built in R, and there we can point on a map, and then we can extract some information. This is not direct aquaculture information, but this is data that we fish from the Blue-Cloud to show some time series of specific environmental indicators that you might be interested in. So all these are R-based components that are for metadata management and spatial data representation are already, so they can be used by this VRE immediately. And then you can, for instance, in this case, build a statistical plot over a region of interest. So we can define tables, plots, and graphs to extract and visualize statistics from the Blue-Cloud and show them in our widgets like this. So the widgets have a strong geospatial focus, so you can click on the map and you can send data about the location into the Blue-Cloud and store them and further process them there. The environmental service behind this also uses a data miner, which is a deep science technology as well, to send OGC requests to different thread services where we collect results, merge, and send them back to the R-Shiny displayed on the map. So that is how the data behind these plots are accessed, brought back to the data miner, and then converted into something that can be represented in an R-Shiny application. So many of these open source components are used and maintained for other FAO products, so which means that maintainability and cost effectiveness can be quite high if you manage to stay close within the other work we do in FAO for this type of data analysis in the fisheries and aquaculture domain. So with this same technology, so deep science technology, we can fish in large data repositories, so we can access other remote sensing data. This is just an example of something we recently did over the Lake Victoria, where we accessed public remote sensing data that are relevant for monitoring of aquaculture in this region through the same metadata-driven approach. So this example shows it's a trivial data set of an area of interest, and with the metadata approaches, so in this case, a trivial metadata data set, but the effort was also trivial. This is done in a very brief amount of time. So metadata-driven geospatial data flows are feasible in the Blue-Cloud. So thanks to the Blue-Cloud efforts, we can now, for instance, put aquaculture in a broader spatial context with little effort. But we also need some caution here, because not all data that are free and open and can be discovered in any cloud are useful, because a lot of data are maybe too coarse for really monitoring use in aquaculture, where sometimes the demand is for much higher resolution than what is publicly available. Another interesting feature that we tested was to overlay our analysis with other public data. So this is just an example. Again, you see an R-Shiny statistical widget pop-up, but now from a OpenStreetMap. So with OpenStreetMap, we can already do computations across our detected locations. You can, for instance, detect in this case, how far is my location from a ferry terminal, so which is important if you want to land your fish or bring some feed or your personnel to your aquaculture farms. We can already tell you a bit about the distances that will be involved if you start developing something. So we use here, this is an example of a public web API to access and compare data. So this makes the results of a deep analysis that CLS made, we can bring this to an audience that is making me be much more interested in, for instance, spatial planning exercises. Rather than doing the complete analysis, we will only bring them the results, and we show the results in context of other interesting data. This was my introduction, so the wider use case scope, why did we do this work? It's research work, it is not trying to solve a specific problem, but we think we are ready to provide you with some services in a cloud environment that can be further developed to meet a specific use case. So thank you for your attention so far. Now, Jeremy, the floor is yours.
Hello, everyone. Thank you, Anton, for the introduction. So I'm Jeremy, a data scientist at CLS, and I highly contributed to the technical part of what Anton presented. And so I am gonna show you a few slides to explain how it works. and what are the inputs and outputs of the whole pipeline. So can you confirm that you can see my screen?
Yes, it's working.
Okay, perfect. Thank you. So just a quick outline. So first, I'm going to introduce the topic, and then quickly go through what the Blue-Cloud service, but Anton already talked a bit about it, so I'm going to go quickly. And then present two use cases. One is about offshore aquaculture, and the second one is more about inland aquaculture. And you'll see these are actually two different types of objects that we try to detect. And so we use two different types of algorithms, but I will present this later. So first, a few words about the CLS. So CLS is a company that was created by CNES, the French space agency, 30 years ago, and has an experience on exploiting satellite data to monitor the Earth. And so we have experience on land, but also on the ocean specifically. So we have some experience to detect cages offshore for mariculture, but also coastal aquaculture and also rice and fish aquaculture, which is more of a land cover approach. And so the goal of this project was to try to find an effective and affordable satellite monitoring of aquaculture locations. And so we have at hand several types of data. So we can either use SAR images. So SAR stands for synthetic aperture radar, which is, for example, Sentinel-1 type of images, which can be really handy because they go through clouds, so they're cloud insensitive. So we can have images. Doesn't matter how the weather is. So images everywhere. So that's really good.
Sorry, Jeremy. Jeremy, one comment. Can you please switch off your camera because
the microphone is
contact,
breaking.
Yeah.
Oh, sorry. Okay, sure. Wait. Yes. Is it better now? Can you hear me?
Yes.
Okay. Well, okay. Let me know if I have to improve. Yes, I was saying, so we can either use the Sentinel-1 data or Sentinel-2, which is more optical images. But the problem is they are weather sensitive. So then we have to post-process them a bit more, but to remove clouds, but we'll see about this later. And so we, in our use cases, we actually use both, depending on the type of a problem that we study. And so, as I said, so a few are problems that we are interested in. The first one is to detect cages, so using Sentinel-1 time series data. And the second one is we detect aquaculture ponds, and we have a use case in Indonesia. And this time we use a time series of Sentinel-2 data. And then we integrated some of the algorithms in the Blue-Cloud infrastructure in the form of a notebook, so that users can directly run the algorithms on their own data. And these are a few words about the Blue-Cloud Virtual Lab, but Anton already talked quite a bit about it. Just the important point for CLS here is that we integrated the algorithm in the notebook, and it is open to everyone. So the first part is the offshore aquaculture. So here's an image to display an example. So it's actually a PlanetScope image here. You can see it's over Chile, and you can see aquaculture cages pointed by the red arrows here. And these are the clusters that we try to detect. And so a few words about the workflow. I'm not going to go into too much details, but just to show you an overview. So there are two pipelines. The first one is how do we get the data and how do we pre-process it? And the second one is how do we process it to actually get the the desired results. So for the pre-processing part, we first, I'll show you a bit more in details, but we first download the images in terms of type series, and then we have apply a few pre-processing steps to, let's say, make them all in a clean data cube with all the images properly overlapping each other with no angle, satellite angle problems, etc. And then we have the processing part where the user has to define a region of interest. So it's a shapefile that is drawn by the user. This is where the user wants to detect the aquaculture clusters. Then we use the time series that was downloaded and pre-processed, sorry. And then, so the first step of the aquaculture cluster detection is to do a water, non-water segmentation. So we just try to differentiate objects that are water and not water. And then we try to remove false positives by applying a landmask and other post-processing steps to only keep the floating aquaculture clusters. Then the output of such an algorithm is a geopackage file with centroid coordinates. And then if we have access to higher resolution images, which are not open source, so we don't always have access to them, but if we have one, like for example a PlanetScope image, we can go into much more details and compute statistics over the clusters, like for example the number of cages, the average size, etc., etc. And so for the pre-processing part, what we use exactly is a library that was developed by a CNES. It's called S1 tiling. And so here you have a screenshot of some of the parameters that the user has to define to download the images. So just the first and last dates of the time series, the tile that gives the location of where we want to download the data. And then the polarization of the SAR image, either VV, VH, or combinations of the two. Then so the download is done, and then 3 pre-processing steps are applied. So first there's a radiometric calibration, then auto rectification, and then tiling. And at the end we have a nice data cube that we can run through the algorithm to get the following results here. So what you can see are some screenshots over Tunisia on the left and Chile on the right. And so in Chile we have 100 plus clusters and a bit less in Tunisia. And you have the performances in the table here on the bottom. And so what you can see is that in Tunisia, we have a quite good precision and recall. So for those who are not familiar with those metrics, they go between 0 and 100%, and the goal is to be closer to 100%. And so we actually quite well detect the cages. In Chile, we have also quite good precision. The recall is a bit less, a bit lower, but still really acceptable. So Chile has a few small islands that can be seen as false positive, as non-moving non-water bodies, so that can be seen as false positive by the algorithms. But in the end, on the whole area, statistically speaking, the results are really good, and we're quite happy about them. And so just to show you the interaction with the Blue-Cloud infrastructure. So here's a notebook. So it's a screenshot of the notebook that we wrote. So basically, there are a lot of explanations of how it works, the pipeline, and all the parameters that the user has to define. And basically, all the inputs have to be put in a file in some folders here on the left, and then you just run the notebook, and at the end you can see all the results that are even plotted on the map directly on the notebook with the region of interest that was drawn by the user. So you can directly check if the results are the one that were desired on the notebook. And then if we want to go further, so as I said, if we have higher resolution images, like for example, PlanetScope image here, so which is a 4-meter resolution, then we can go further and compute statistics over the images. So the first step, we have the cluster centroids. We can use them to download images over the detected clusters, so that we don't have to download the whole tile, which is quite big, but we can really target the clusters to download really small images, which is less expensive, of course. Then we have the PlanetScope images that you can see on the right here. And then we apply a few image processing steps to be able to count the cages. Like you can see here, one color per cage. And then we can even find the contours of those cages. And then once we have this, we can obviously, knowing the resolution of the image, assess the size, the average size of the cage, etc., etc. And so the final result looks quite nice here. This is over Chile, where you can see that we don't have only the centroid of the clusters, but we can count each cages here. So that's actually quite nice. So in terms of conclusions for this first use case, so we tested the algorithm over several regions. So I showed you Tunisia, Chile, but we have also Greece, for example, with good precisions. So for the use case, it is enough to monitor large patterns in marine aquaculture, because we're interested in statistical evolutions over time. So that's enough for this goal. And yeah, well, that's pretty much it here. And then, I will give some time for questions at the end. Just to finish with the second use case. So this is more about inland aquaculture. So you can see that the images are quite different here. All you can see on this image here are aquaculture ponds, so they are different objects. They're not isolated objects in the sea. Here we're on land, and there can be mixed with other crops or other types of lands, like houses, which are really nearby. There's here a river, etc. So this is a different type of problem that requires another algorithm. And so the approach here is more to use our land cover expertise that we have at CLS to detect those ponds. And so this is actually a machine learning approach this time. So what we do is, as I said at the beginning, we use optical images and not radar for this use case. So we have to download the images, so Sentinel-2 time series. Usually 1 image per month for 12 months is quite good, so that we can have an overview of what's happening. I mean, where are the ponds on 1 year. So we have a L3A, sorry, type of Sentinel-2 images. So we have a stack of time series, and then we have a database of labels that was done manually by some experts. So basically, that's when we say, well, on those pixels, there are buildings. On those pixels, there are aquaculture ponds, here water, etc. So we label a few pixels, and then we train machine learning algorithms to automatically find by itself to understand the relation between the images and the labels that we gave them. So that then when we give the algorithm new images, it can automatically predict what it sees and classify every pixel. So the output is a map that you can see here at the bottom. Well, yeah, there's a bigger one here. So it's over Indonesia. And what you can see is, for example, in red, we have the city, so built up areas. But what we're interested in the blue cloud is in purple. So those are the fish ponds. That you can see like a very, very big area of fish ponds here at the north. And then you can see all vegetation, land cover type of stuff like trees, forest, etc. There's a lake, but again, what we want in Blue Cloud are the aquaculture ponds. And so in terms of performances, well, Tarunamulia is gonna speak next to present some validation that he made on this data. But here's an overview of the accuracy that we had, about 72%. Which is quite good. And I think that, yeah, sums up my presentation. I can take some questions at the end of the webinar. And now I can leave the floor to Tarunamulia for validation.
I think Tarunamulia, you are still muted.
Yep. Hi, everyone. I'm Tarunamulia from National Research and Innovation Agency, Indonesia. Thanks, Anton, for the nice introduction. And I would like just to continue what Jeremy last slide talking about. So I would like to talk about the accuracy assessment of artificial intelligent generated maps of aquaculture ponds in South Sulawesi province, Indonesia, which is actually produced by the CLS France under the Blue-Cloud, and trying to explore its potential application, especially for coastal land-based aquaculture management. Okay, sorry. Just a little bit introduction. So geospatial information is now very popular and has become an integral component of natural resource management activities worldwide. And in aquaculture programs, it provides general spatial decision support for site selection and suitability assessment, monitoring of aquaculture changes, and environmental impact assessment. In fact, with the existing remote sensing technology, academician, remote sensing analysts, and including me, has experienced how difficult it is to delineate aquaculture ponds in coastal areas. It is not only challenging using the technology, but also expensive and time-consuming. Luckily, CLS France has developed an innovative remote sensing-based image classification method using free Copernicus or Sentinel 2 optical imagery. Our purpose here is that the AI-based map are expected to accurately map the coastal land uses, such as aquaculture ponds and rice fields. Of course, no one will expect that the image classification is error-free, for sure. However, since the map will be published worldwide via Blue-Cloud Aquaculture Monitor (PRE) and potentially adopted by some countries, so I believe that it is necessary to assess the accuracy and as well as the validity. So Thanks to Blue-Cloud and Jeremy CLS for selecting South Sulawesi as the study site. So the AI-based map was validated for South Sulawesi using the ground truthing. It's about 700 randomly selected data points within the 10 to 18 classes for the ground truthing. So the total area, it covers about a total area of 12,000 square kilometer, which is, it is times larger than Rome, the total area of Rome, or 1/3 of the Netherlands area, I believe. So in terms of accuracy or error assessments, it was conducted through two major steps. Firstly, by visual validation, we compare the CLS map classification against fileable maps. And secondly, by confusion matrix, we examine the 700 reference points using existing field data and no local, and using our own local knowledge, and with the help of high resolution such as Yandex or Google Earth imagery. So the validation process was conducted with the help of Quantum GS software, which is open source software, GS software. We search and inspect point by point and tabulate the result into the confusion matrix. This is just to show how we validate the 700 point. In this case, we employ point-based sampling unit, but the problem here is that it is difficult to find exact pixel single locations. So to compensate the weaknesses of the point-based approach, so we also perform area-based sampling with using radius 30 meter using 3x3 pixel, also called the proportion method. So, and the level of accuracy assessment was done summarized in error matrix, and the level of accuracy was evaluated employing 3 standard statistical measures: overall accuracies, producer accuracy, and user accuracies. So this just to show the the confusion matrix, just to summarize the overall accuracy as well as the confusion between individual classes. So the column here, the column represent the reference data, which is the reference data that are assumed correct, and the rows indicates the classmate generated from the remote sensing data. So, and the diagonal of the matrix summarize those pixels or points that were assigned to the correct classes. So, and based on the analysis, the overall accuracy for the LC map was 71.6%, as Jeremy mentioned in his last slide. And the accuracy for the specific cover types range between 35 to 99%. Some bare soils, rain-fed rice, river, canal, and mangrove classes were particularly difficult to map based on my analysis, and attain accuracy below 50%. However, the lower accuracy were not unexpected, because for several reasons. The reason for the poor outcome might be due to some sweater overlap between the classes, and also maybe because the training sample pixel and sample size are small in this case. I'll take for example here, rain-fed rice and grassland can easily be misclassified as barren soil, particularly during dry season. This is because during the dry season, rain-fed rice become very dry and less vegetated. So also river canal was also often misclassified as lake and fish pond, maybe because it has the same reflectant failure. And also shallow water was misclassified as fish pond, but this is something that we were expected. We cannot actually rely too much, considering the spatial resolution. of the Sentinel-2. So looking into more detail, so based on the producer and user accuracy, take for example, rice paddy, although 90% of rice field pixels were correctly identified as paddy rice, only 44.26 of the area is called paddy rice, actually paddy rice. And producer's accuracy and user accuracy for fish pond is relatively constant, 70%, which is actually good, quite good. And then it's just to show how we actually we conduct point by point inspection. So this is, for example, some misclassification rice field. This is during the dry season rice field, which is classified as aquaculture pond, and this area is supposed to be a rice field, which is then classified as secondary forest, and the down here, left down here is actually should be grassland, but classified as a bare soil. It is actually classified as grassland, but it's actually bare soils, and grassland. It is the last picture, which is grassland, and then classified as rain-fed rice field. But this is something that we expected. So just actually to summarize key points, that there are some problems, but it's not actually a big deal. To some extent, we'll not be able to effectively separate or distinguish specific categories, such as ponds and coastal mud, ponds and canal, and ponds and neighboring rice fields. There are some ideas to improve here. Actually, it's like you need to consider seasonal operation, like multi-season image classification, and need to incorporate ancillary data such as SRTM, coastline, hydrology maps, like canals or river. We can just actually cut these kind of things and landform maps in order to improve the quality. Also, the last thing that we can obtain multi-years or season of high spatial resolution remotely sensed data to improve the selection of training data. So some potential application of this map is actually we can use this map for extraction of pond area, defining existing and potential area. But it is actually applicable for national and provincial coastal aquaculture development and management. We can also use for identifying land habitat conversion due to pond construction or saltwater intrusion, and land use cover chain detection, or more importantly, potential conflict of land uses using multi-years or seasonal operation. This is some example maps that have been adopted by local government just to inspire and other aquaculture stakeholders in Indonesia. With this maps, we can actually identify changes of fish pond areas at specific period of time. For example, the total aquaculture pond increased in 2002 by 2,500 hectares in Maros, and also see 6,000 hectares in Pangkep. Is something that kind of application we can think about in the future. Another application, you use multi-season image analysis to understand seasonal variation of land use as well as land suitability for coastal land-based aquaculture, because it will actually show a significant difference in terms of the the area and as well as the quality. And this is what I have done to actually this is nothing. It's not really correlated to the image classification, but we use image the output to image classification as the input layer input for quasi-logic analysis. So this is to help estimate the potential extensification of aquaculture pond, but we need actually some more environmental data like a tide analysis, and then we can also identify water availability and combine it, then use it to estimate the potential extensification. This is just to actually to introduce different types of coastal land-based aquaculture in Indonesia. We know we have extensive aquaculture pond, also extensive aquaculture pond, which it will very likely difficult to differentiate using the image analysis, coarse scale image analysis. And also recently we have what we call millennial shrimp pond using different circular shrimp pond, and some using intensive aquaculture pond using HDPA, geomembrane linear, or like a plastic cover. So, and another idea for future direction actually in Indonesia to compensate for the lack of data for the management for farm level basis. Of course, the Sentinel cannot do this, so we develop like WebGIS to provide more detailed information for pond management, and then something like that we use freely available Google Earth. So we make a link with Google Earth, and then we ask farmer to input farmer extension officer or student to provide to update data. We can actually map the agro inputs like fertilizer, to map the fertilizer, lime, or other agriculture or aquaculture inputs, the availability, and also types of agro input available. And in this, for example, when we click this spot, then we can know more detail about the quality of land. We can understand who is the owner, what's the soil quality, water quality, what kind of species culture, and then the requirement for aquaculture input, something like that. So yeah, I don't have a specific conclusion here, bullet point conclusion, just very general conclusion. I believe despite some misclassification or conclusion, the match classification method demonstrated by CLS still within the acceptable level of accuracy, and I believe it's very useful for spatial planner, particularly for aquaculture, coastal land-based aquaculture stakeholders. And overall, the AI-driven image classification approach demonstrated in the study provides adequate information for national and provincial aquaculture planning purposes. So to improve the quality, the multi-year S2 images will have enhanced locality and the application of AI-driven image classification. I think that's all from me. Thank you very much for your time.
Okay, thank you, Tarunamulia. That's a nice overview. I'll switch my camera on. Well, thanks to all the participants. There are a few questions already. But first, my thanks to Jeremy and Tarunamulia again for making these nice presentations, where Jeremy went into the cloud, showing what is done in terms of technical work to detect cages, and in terms of machine learning and artificial intelligence work to detect the aquaculture ponds over the area, where we have an expert from Indonesia working with us to validate the outputs, and also showing how far they have already come in Indonesia with setting up a very extensive register of aquaculture farms that includes much more than only remote sensing data. So we think you need both. You need to look from above, you need to have feet on the ground, and then with that combination you can help farmers, but also help management to improve the resilience and productivity in the aquaculture sector. So there are a few questions, so I will try to do my best to answer them, and then somebody else can jump in the pond to improve my answer. So the first is from Jean-Pierre Kozak. I lost my glasses yesterday, so I cannot read the question, but as far as I remember, with my crappy glasses that I have now on, the question was, so we had in one of the slides, we showed a pop-up where we showed some time series of environmental indicators that we detected over a map. So we went, you click on the map, and then we have a pop-up that we can generate a pop-up in an R Shiny application that shows some environmental variables, how they developed over time. The specific question here was, so there was in the reference, we saw in green a line for an item for chlorophyll, but in the graph itself, we do not show any chlorophyll. And the question is if there is work done in FAO to be able to get chlorophyll values from brackish waters, and murky waters, which are very difficult to compute from an image. So you have an image that doesn't tell you nothing about the chlorophyll. It tells you about the color of the water. My short answer is no, and my long answer is there's probably some activities going on to improve the assessment of chlorophyll in coastal waters, probably also in FPO, but I'm not aware of anything recent, so I cannot give you a complete answer now. But I think what we tried to show is that yes, we can, from our infrastructure, we can show you with a metadata-driven approach. So even if there are labels, we will show the labels, but if there's no data behind the labels, our metadata-driven approach will show the label, but it cannot give you the data because the data were not given in the source information. Is that a complete enough answer, Pierre, or you want to learn more? Okay. Then there was another question. If we used the FAO has a big collaboration going on with the Norwegian government, where Norway really gave FAO a huge amount of geospatial data. And yes, we contacted them and we did an experiment with the data. So what we did in Blue-Cloud is at an experimental research level. So it's not an official FAO output or FAO product. It is really a Horizon 2020 research project. And as such, we asked for data. People were nice enough to help us with detecting some information. We also worked then to analyze the data, which if I remember correctly, Jeremy can jump in the ocean here because it is about the data coverage over marine waters, and the marine waters, the calibration there was a bit poor. So we had some issues with the image quality over open ocean areas. And that is not because the data are per se bad, but because it was difficult to get calibrated images of the areas of interest where we wanted to detect cages. Is this correct, Jeremy, what I said? Or?
Yes, yeah, that's correct.
Yeah. But very helpful people, both from the CPAL team in FAO and from planet.com, the global outreach team that were really trying to help us with getting better calibrated images. But we failed to get them, so we had to stop. So what we do now, we had to stop at the detection of the cages. So Jeremy explained what the next phase would have been. If we would have higher resolution optical images, we could compute geospatial statistics, so the number of cages, the total covered size by cages, the average size by cage, etc., etc. But since we had so many problems with the image quality, we decided to stop it and show you some initial results. But with better images, we would have had better results. But we can do it. But since it was not a huge task in the Blue-Cloud project, we decided to move on land and continue focus fully on the artificial intelligence and machine learning algorithm. Okay, are there more questions?
So there were a couple for Tarunamulia, but I think he was typing.
Okay. And there's also, so can you describe a question of Mark? Hello, Mark. Mark is a team leader, and no presentation is complete without mentioning all Mark's effort to build this information and knowledge management team here in the Fisheries division in FAO. And he asked if we can describe the type of user that can interact with the interface of the aquaculture detection lab, and what users are able to do using this interface. So we really have work in a collaborative environment, which means people can collaborate. So we have a huge platform, the D4Science platform, where you have a single sign-on. So after you sign in, you can then be assigned different roles. So we have very technical roles in this platform where people work to develop, for instance, a Jupyter notebook that requires that you know some coding and that you can develop a Jupyter notebook. But a Jupyter notebook can then be This is just one example, so there's other ways to interact. But the Jupyter notebook can then be given to a person with much less expertise in making or accessing the images, but that user can then change some of the parameters in the analysis, so it can move to a very rather simple, maybe to a different location and to do the same analysis in a different location. So that is already one step where developers or deep core developers can interact with by intermediate level developers to help them to set up a workflow that then an intermediate level user can then customize to, for instance, a different area or a different type of classifications of cages. Then there is a third level of users, and that's really the end users that only interact through a visual interface. So we showed examples of how our Shiny apps can already be used to extract information from the Blue-Cloud and show these in, for instance, statistical widgets. So a lot of R coding there, done also here in FPO in-house, but then brought into this virtual research environment. So users have statistical pop-ups, reading data from in this case, a spatial data infrastructure, and exposing those to end users that the end users can then download as images or include in screenshots, etc. Okay, that is hopefully enough to explain a bit the different types of users. So core developers, then application developers that help people to extract data from the Blue-Cloud and other infrastructures, and then end users that interact with final products. And this we go back to the Q&A. There's 2 questions for Tarunamulia. Maybe Tarunamulia, can you answer the questions? So maybe I do go first, and there is a question from Miss Momiba Chiyoka. So welcome, Chiyoka. Long time no here. Good to have you back. Yes, thank you for the presentation. How effective would be the technology for an inland country like Zambia, where most of the fish farming activities are done on land? So you can detect anything even if you lose your keys. In theory, you can detect them with a satellite image, but the costs there are very, very, very high. So if we look at a country like Zambia, where you have, for instance, on the lakes, you have some floating cages, we can already detect them. Jeremy already made that analysis, and we could detect most of the cage clusters on the lake. But then for the smaller inland farms, they will always be difficult. I think with Tarunamulia, you might have a discussion how they approach it in Zambia to detect really small cages. I think you have to go to get feet on the ground and really ask people, because you're not only interested in where a cage is, but you also want to know how it is used and what it is used for in production. So with a satellite image, you might be able, and will be difficult to detect small ponds. And it is really at the limit of what you can do with Sentinel data. If the cages are smaller if the ponds are smaller than 15 meters, it is already very difficult to detect them as an aquaculture pond. If they become bigger, it can either be a pond or like a small dam in a small river. You really cannot tell from a satellite image how it is used. You can only identify its location, and then you will have to go there and do a survey in the field for yourself. At least that is the status of the technology. In our case, there might be other approaches that have cracked the issue, but for me, I'm not aware of a good approach to really detect inland ponds and classify them in a correct manner. I hope that's enough of an answer. Are there more questions? Okay, then thanks everybody for joining this hopefully interesting side event of the Science and Innovation Forum. Special thanks to Trust IT, that is also the coordinator of the Blue-Cloud project, for hosting the Zoom event and helping us with getting the slides smooth and safely presented to all of you. And all the participants, of course, welcome for any follow-up questions that you might have. You know where to find us. There's also now already in the chat the location of the recording that will be made available through the Blue-Cloud website. And then, so thanks also to Mark Takonet again and my colleagues in FPO that really worked very hard to make this a success. Thanks to Jeremy, thanks to Tarunamulia again. All the best with your future efforts and endeavors. And then hope to meet you again someday in the not too far future. And any questions are welcome to drop in our mailboxes. Okay, thank you.
Thank you.